Thank you everyone for joining. Today I will be giving a talk titled Build Snappier Apps with React and Web Workers. Obviously, given the title, we're going to be talking about web workers and a little bit of React. So if you're not a React developer, this is still very much also applicable to vanilla JavaScript or any other frameworks. But once again, thanks for tuning in. I'm excited to be here. Lots of tough acts to follow in this event, but I'm excited to close it out. So without further ado, I'm going to go ahead and get started. I will tell you a little bit about myself first. My name is Mehdi Vasigh, and I'm a senior engineer at MailChimp. And I'm into lots of things. I do a lot of front-end development, obviously, but I'm also a creative coder. I'm online on Twitter fairly often, so if you wanted to get in touch with me, look at some of my work, or just chat with me about anything, please feel free to reach out. I love talking to people. So before we get into talking about web workers, I'd like to first talk about performance and what it means to have a high-performance web UI. So traditionally, when we talk about web performance, one of the topics, or really the topic of web performance historically, has been around initial page load. So a lot of the metrics that we have when we measure performance, such as time to first byte, or first meaningful paint, or time to interactive, including also like things like Lighthouse scores and Web Vital scores, have to do a lot with the initial page load of your web page. And this obviously has many contributing factors, among them both like the server that you're using and server performance, as well as the assets that you're delivering to the browser and how they're being interpreted. However, historically, afterload web performance has not been as much of a main topic in the web development industry or community. It's a new concept to the web because historically web applications have not been as rich or as interactive or as animated as their native counterparts. So what do we mean when we talk about afterload performance? Afterload performance has to do with things such as smoothness. So how smooth or how responsive to interaction or how interactive your application feels. I also touched on obviously responsiveness. So when you click a button or interact with an element, how long does it take for the application to respond to your interaction and give you some kind of feedback? As well as things like memory efficiency, battery usage, how much of an impact your application and just running your application is having on the user's device. These are all user experience factors that we don't typically measure in the web as much as we do the initial set, the initial page load, time to first byte, first meaningful paint. And part of that is because it's just not as fully developed. There aren't as good metrics for measuring. Some of these things don't actually have very good metrics at all for measuring. And it's also very difficult to come across tools and existing kind of frameworks of thought in the ecosystem for doing this. So today we're going to be focusing predominantly, actually almost entirely, on after page load performance, and specifically on the topic of smoothness. And so smoothness means maintaining a stable frame rate. If you're a gamer like me, or if you enjoy interactive media of some sort, you know that frame rate is very important. It's kind of everything when it comes to suspending your disbelief and believing that the interactive media that you're viewing or the game that you're playing is immersive and is smooth and it's an actual living thing in front of you that you can interact with. So there's a concept that I'd like to introduce when it comes to smoothness and the frame rate, which is the frame budget. So you might also, this is a number you might have in your mind if you're a gamer, but in order to produce animation that's perceived as being very smooth, typically we want to target around 60 frames of animation per second, and we want to keep that as stable as possible. Now you might notice there's an asterisk next to this sentence in my slide, and that's because the browser doesn't always actually paint exactly 60 frames per second. Actually, what the browser typically does is when there is no need for producing new frames of animation, so when things aren't moving, when there's no animation, it's not producing new frames because it's just an optimization that the browser does. But from a mental model standpoint, or conceptually, you can think of animation as having to be 60 frames per second to be successful. So the frame budget is effectively how much time you have to produce one frame of animation. And you can get this time with some simple math here that I have. I know this is math is scary for me as well, but hopefully this isn't too much. So if we have 1,000 milliseconds in a second, and obviously if we want to produce 60 frames per second, if we just divide those we get 16 milliseconds per frame that we have. That's basically the budget that we have, the time that we have to produce one new frame of animation. Now, this can't all be our JavaScript. The browser also does quite a bit of work, obviously, to produce a frame in the browser to paint. That includes modifying the layout or the structure of the page, understanding and kind of like parsing and computing styles and painting those to the screen. And then so the combination of this typically takes, you can approximate around 4 to 6 milliseconds per frame for the browser to do the work necessary to paint your application to the screen. So what that means is all of the JavaScript that we have, or like the time that we have available to us to run all of the JavaScript necessary for our application to produce a frame of animation or to produce some UI that's necessary to be useful is about 10 to 12 milliseconds per frame. And again, this is a generalization, but it's just a good mental model to have. And obviously, like if you're building a very interactive animation, you want to be on the conservative side of this. So now let's talk about what happens if we exceed the frame budget. This is a chart that you might be familiar with if you've used the performance tab of your Chrome DevTools, or if you've just looked at web.dev or any articles around the browser pixel pipeline or the sequence of steps that the browser goes through to produce the actual web page that you see on your screen. But the pixel pipeline for the browser typically looks something like this. I've color-coded these sections to match what you would see in your browser's DevTools, but essentially you have multiple steps that the browser goes through, the first being executing any JavaScript necessary. There is 2 steps called style and layout that are somewhat self-explanatory, and then a paint and a composite step that occur at the end that actually produces the end result. Some of these steps don't actually happen every time the browser paints anything. So style and layout, for example, are 2 steps that can be skipped if certain conditions hold true. This is to kind of relate this to your experience that you might have had. If you've ever heard of the best practice that you should use CSS transforms rather than animating the top and the left position properties in your CSS, that's because by using transform, you would avoid a layout reflow and you would be able to skip 2 steps of the pixel pipeline and you would essentially have a more performant animation. So there's a website here. I will share these slides as well in the discussion after the talk, so you can check out all of these links. But this website, csstriggers.com, has a very comprehensive list of all of these CSS properties that you might use in your styles and how they impact the browser pixel pipeline, or specifically what steps can be skipped. So I mentioned that all of our JavaScript has to live here. And if you are building applications with React or another front-end framework, you know that it's very common to see React applications that consume everything. So have everything under the umbrella of the React application, and the React application is really the root of your entire experience in many cases. So what that means is all of your UI and local logic, UI state, all of your components, as well as if you have a CSS and JS runtime, so for example, something like styled components, as well as your front-end framework itself. So if you're using a framework like React that has a runtime and does all of like the wonderful virtual DOM stuff that it does in synthetic events, and if you're using a state management library like Redux or MobX, all of this JavaScript has to live inside of this yellow square, inside of this JavaScript rectangle, rather. It's not a square, but inside of this step of the pixel pipeline. And what can happen is if you're running too much JavaScript and trying to produce a frame at the same time, if your JavaScript exceeds that budget that I described earlier, you might introduce jank by dropping frames in your animation. Now, obviously, this diagram is a little bit exaggerated. I'm not intending to imply that just by using React or styled components, you're going to exceed your frame budget, but it's kind of a simplified illustration of what can happen if you are adding many layers of your application in JavaScript, and it's just something to be aware of as you're planning and architecting your applications. So of course, the more JavaScript we add, the deeper we go off of this kind of red line that I've illustrated here, and the more frames that we drop, because the browser has to essentially play catch up. So if your JavaScript exceeds your frame budget, the browser will then have to ignore subsequent frames and catch up on a later frame, dropping the frames in between, and you would introduce visual jank in your animations. So here is an example that I have, and let me actually make this a little bit larger. And I'm actually, for this example, I'm going to open up my DevTools. Now, this mini application that I have on the left here is it's kind of a rudimentary Fibonacci calculator. So it's recursively calculating the Fibonacci number at some sequence. If you're not familiar with the Fibonacci sequence, it's a sequence of numbers where each number is all of the previous numbers added together. So this is doing the work in a very unoptimized fashion, only to illustrate some blocking code or some code that can introduce jank. And I'm going to illustrate that using the browser's DevTools. So I happen to know that there is a specific number that I can use that will lock up the application just long enough for it to not crash my browser, and that number is 42. So I'm going to record my DevTools performance tab, and I'm going to type in 42 and hit calculate. And you see now that this bouncing ball animation that I had has completely stopped. And these are all frames that are being dropped. And finally, the work is done. And the work took about 5.5 seconds. So I'm going to focus on this frame, since this is actually running in an iframe. This is our browser's pixel pipeline, essentially illustrated on a flame chart. And I want to show you a couple of things. One is that these are frames of animation that are being computed and painted. And you can see that they're very evenly spaced apart. This is what I meant initially when I discussed having like a stable frame rate or something that's very regular and consistent. And you can see that in the smooth animation. And then, of course, when we get to our blocking task, we have a giant function call that takes about 5.5 seconds that blocks our main thread and introduce jank in our animation and stop the ball from bouncing. And of course, afterwards, the browser had to play catch up. So this was just an example illustrating what it means to drop frames and block the main thread of your JavaScript, thereby introducing jank. So if you're keeping up with React news, you might be thinking, isn't this the same problem that React 18 is solving? To give you some context on React 18, React 18 introduces a concept of concurrent React with something called a transition. And what this allows you to do is essentially set some state that's not as important or lower in priority than some of the critical parts of your application. So things that are very interactive. And this allows React to then defer rendering the unimportant or higher, or rather lower priority items in favor of the higher priority items. What this is intended to do is keep your application more performant by keeping it more interactive and avoid blocking interactivity when you're trying to perform a lower priority update. However, this is actually a different concept than what we're going to talk about with web workers. So in order to talk about that, I have to talk about concurrency and parallelism. If you're not familiar with concurrency and parallelism, I hope that this diagram can give you a good example or visualization that might help you. But the concept of concurrency means essentially being able to interrupt work. So here we see one CPU core concurrently doing two tasks. And in this case, task 1 and task 2 are perceived to be happening at the same time. But in reality, what's happening is that the CPU is performing some of task 1, interrupting it in favor of task 2, and then interrupting that and coming back to task 1, and so on and so forth until both of them are completed. This is actually how all of JavaScript works in a single thread. So if you're using promises or timeouts or callbacks, this is the entire point of the JavaScript event loop, and this is how concurrency is handled in JavaScript. The concept of parallelism is a bit different, and parallelism, means truly doing two different things at the same time. So here we have two CPU cores, and they are performing task 1 and task 2 simultaneously without actually interrupting each one of them. Now, in this example, the two tasks complete before they do in the concurrent example. However, this isn't always the case. It's just kind of a way to illustrate what this looks like. So I touched on this in the previous slide, but we talk about JavaScript being single-threaded. And what does that mean? Well, what it really means is that JavaScript, typically when we work with JavaScript, we are working inside of a single execution context. And we can refer to this as the main thread. And this execution context is where all of our code runs. If a function takes too long to execute inside of this execution context, it will actually block all of the subsequent code or all of the subsequent functions. And what that means is that none of those following functions can execute until this function is done. So everyone is sharing resources inside of a single thread. So an example of blocking code is a simple while true loop. In this code example that I have here, we have a while true loop that doesn't have an exit condition, and this is obviously blocking. And the downside of this, of course, is that our extremely important function here on line 6 will never execute because this loop will never run to completion. So this code is blocking, and that's what we mean when we say blocking code. So enter web workers, and really the purpose of web workers here is that web workers allow us to take some blocking code and execute it in a separate thread in order to unblock our UI thread. So when we're building an interactive application, we really have to treat our UI thread as the most important resource because it's what keeps our application free of jank and interactive and responsive to the user. So sometimes when we can't avoid blocking work, when we have to do some computationally expensive and blocking function, it's beneficial to us to do that in a separate thread in order to not share resources with our main thread. I've added a note here as well. Web workers and service workers are commonly confused with one another. And I wanted to mention that web workers are not the same as service workers. Service workers are another type of worker that's offered in the browser it's essentially a reverse proxy and used for things like offline capability. But web workers are although they are conceptually somewhat similar, they're actually very different in usage and in practice. So let's go back to our bouncing ball example here. And I'm going to once again open my DevTools. And you might have noticed this earlier, but there is a non-blocking option in this example application. And this time I'm going to record my performance when I use the non-blocking version of the Fibonacci calculator and see what we see. So I'm going to type in 42, calculate. And you might notice that the ball is still bouncing. We're calculating and the ball is continuing to bounce. The animation is not interrupted, and then our work is complete. It took a little bit longer, and that's not necessarily because we ran that's not necessarily because we're using a web worker, but sometimes that can be the case where your work might take longer to run in a web worker. Of course, the trade-off being that your application's animations don't get interrupted. So let's visualize what happened here. Here we have our frame execution context once again, and you might notice that all throughout we have our frames of animation being computed and executed and painted without any kind of interruption or blocking. And then we have a worker frame here, this execution context. And this is, you might notice, this is like a separate JavaScript file entirely. And the only thing happening here is our long blocking 5.79 second function that produces a number, right? So this is good because we are no longer sharing resources between the interactive part of our application, which is our animation, and our expensive function, which is our Fibonacci calculation. Cool, so let's talk about web workers and really what they are, what they look like in practice and in code. So web workers are objects in JavaScript that have their own execution context. They don't share any memory with the main thread or with other workers. So if you've used threads in other programming languages and have written code that's multi-threaded, you might be used to having some kind of shared chunk of memory that your threads are all acting upon. That's not the case when you're using web workers, and workers actually communicate with one another and with the main thread using messaging and the post message API. So every time that you want to talk to a worker from your main thread or vice versa, you would have to use post message, and then inside of the context that you're talking to, you would be listening to the message event and then doing something with the data that's passed. I also want to mention that data is copied and transferred between threads, but it is not shared unless there's a specific type of object called a shared array buffer that can be shared between workers, but it's not widely supported and it's not easy to use typically. It's very kind of niche. So for the most part, for all intents and purposes, we can consider workers to not share any memory with one another. Browser support for web workers is very good. Web workers have been around for a very long time. So as you can see in this diagram, all major browsers and even Internet Explorer going back to version 10 support web workers. So this is an API that you can really use pretty much anywhere. Very, very unlikely that you would have a constraint that would block you from using web workers in your application from a browser support perspective. And then, so of course, like enough conceptual and fundamental stuff, let's look at some examples of code and see what this looks like in practice. So I mentioned earlier that workers have to be in separate execution contexts, or they create separate execution contexts, but also another detail of using web workers is that when you create a web worker instance inside of your application, the browser actually expects a completely separate JavaScript file to run as the script for that worker. So in this example, and I hope that you can see this, the code that I've added here, you can see this top section is called worker.js. So everything from line 1 to line 10, you can think of as being in a worker.js JavaScript file. And then everything else down here from line 12 on is in a main.js file, or again, a separate JavaScript file. So this is a code illustration of the same diagram I shared before. Inside of our worker.js, we're creating a function called handle message. This is just going to be a callback passed to our event listener here. So we essentially invoke self.addEventListener message to listen for the message event and pass the handle message function. This message object is going to have a data property that's going to contain anything that we pass to or send via the message or the post message API from the main thread to the worker. So event.data is going to check to see if there's a string called ping inside of that property. And if so, we're going to post message back saying pong. In our main thread, we are creating a worker instance by passing in a file name for this worker.js file that I mentioned earlier. Once again, we're adding an event listener for message and just console.logging event.data. And then lastly, we are posting a message with the string ping, which like we saw earlier, we are checking for here. So essentially, this is kind of bidirectional communication between a worker thread and a main thread. And this is the foundation of everything you're going to do with web workers. So everything is just going to be an abstraction over post message and just this communication mechanism. Now, I want to talk about post message really briefly before jumping ahead. So post message is, like I mentioned, data is copied between the two execution contexts. So every time you post message, your message is actually serialized on the sending end and then deserialized on the receiving end. What this means is that there's some work that's done on either end of that communication. However, the algorithm for serializing and deserializing messages is not just like a plain JSON.stringify. You can pass different types of objects, such as like regular expression objects or some of the other like blobs. You can transfer blobs and file objects from one thread to another. So you do have some more complex types that you can post message back and forth. However, there are some limitations to post message. So for example, you cannot share state between the two threads. So you can't just pass like a class instance or a function from one thread to another using post message. And you would run into an exception if you tried to do that. I mentioned earlier the requirement for having a separate file for your worker. Now, this is a bit of a challenge because typically we're used to our bundlers producing like a single bundle or maybe multiple bundles if we're lazy loading different pages of our application. So it's a good idea to basically look at some bundlers and see how they would make your life easier by making workers easier for you. One example that I've added here is Vite. So if you haven't used Vite, I highly recommend it. It's wonderful. It's a great build tool, but it comes with built-in support for web workers. So you can just add this question mark worker to the end of like a relative path to a file. And that allows the bundler to essentially parse that as a worker and allows you to instantiate the worker using this constructor. Parcel does something very similar. However, it just allows you to pass a relative path to the worker constructor, as you can see here on line 14. There's also support for web workers and other bundlers such as Webpack. You just have to kind of do a little bit of digging and searching and research and figure out what plugins make sense for you. One wonderful thing that you can do with web workers is because post message is just an asynchronous API, you can essentially treat worker functions as any other async code in your application, such as data fetching code. And one really lovely library for managing async code in React land is React Query. So if you're not familiar with React Query is a library that provides a use query hook that allows you to essentially manage or abstract away all of the state management that goes into writing async code in React and just use that asynchronous resource directly. So here, what we've done is created a function called render markdown to HTML that creates a promise that resolves when our post message communication is completed. So essentially, we're wrapping over post message with a promise. And then what we can do is just pass this function to our use query and use it as we would any other asynchronous function. Another neat thing you can do with web workers using a library called comlink is to abstract over post message in a different way and make it so that your off-thread objects or class instances, or essentially like you can instantiate workers and treat them as local instances. And so what comlink does is, again, abstract over post message and allow you to wrap your worker and wrap the worker instance on either end of that post message channel and essentially treat your class instance as if it's a local instance. So here we have a class in worker.js that's being exposed via comlink. And then here in the main thread, it's being wrapped and used asynchronously using the await keyword. So really quickly, to close out the talk, I want to talk about when to use web workers and when it would be good to look for them as a tool in your application. So workers are really ideal for whenever you're using or doing something that's very CPU intensive, or when you're working with a lot of data. I've seen web workers be effectively used in things like autocomplete or combo box inputs when you're filtering a lot of data and trying to produce some suggestions to the user. Because if you're just kind of writing a naive filtering mechanism and you're iterating over lots of records every time that the user types a keystroke, sometimes we use like debounces and things like that for this. And web workers provide a better experience because they just provide quicker results without blocking the UI at all. Of course, image processing is computationally intensive, and that's a good candidate. And anytime you can do things in parallel, that's also a good example of when to use web workers. And of course, if you detect that frames are being dropped in your animations, that's a good idea to maybe look at web workers to see when you can offload some blocking work to a worker thread and free up your main thread. Some examples of when not to use web workers are if you have some work that is IO bound. So if you're talking to a server or an API, using a worker is not going to help you, even though those APIs are available inside of workers. Also, the web worker API does not have access to the DOM, so you can't perform any kind of DOM manipulation, and any kind of DOM work that you're doing must be in your main thread. And then also there are some APIs such as local storage that are not available in the worker global context. So if you have something that uses browser API specifically that you're not sure about using in a web worker, I would recommend MDN as a good resource to see if those APIs are available in a worker context. Notably, local storage is absent, but IndexedDB is available if that's useful for you. And also, lastly, I would say prematurely is another example of when not to use web workers. It does add complexity to your application, so if your team isn't on board or if you think it would just make things harder, it might be a good idea to avoid them. All right, and that's it for my talk. Thank you so much. I will be sharing these slides inside of the discussion channel, and I'll look for any questions. If you have any questions, I'm happy to answer them. And if not, if you think of any questions later, please feel free to reach out to me on Twitter as well. Thanks so much.